Good Friday morning, backyard naturalists, friends. It is March 25th, which means we're solidly into the spring season, whether you mark spring astronomically because we passed the equinox or meteorologically because it feels like spring in Wisconsin. Just a couple hours ago, it was cold and wet and cloudy. And when I woke up, or when I was woken up this morning, it was a damn robin singing outside my window before 5 a.m. Reminded me that spring is here. And my name is Tim. I work at the Urban Ecology Center in Milwaukee, and I'm excited to spend the next half hour with you to take a closer look at the very foundation of our backyards today for Backyard Naturalists. All of the critters that we've mentioned here, featured over the years, all of the plants, the insects, the animals, the processes, the weather, everything, they're all made possible by the soil that lies underneath the grasses, the flowers, the trees, the plants, the trees, the mycorrhizal relationships. They all need soil as a medium. It provides structure for the most complex food webs on the planet, and also the basis for all of the food webs on the planet. It provides nutrients needed for life to exist. So we'll talk about soil here in episode 26 of season 3 of the Backyard Naturalist. Double soil and trouble. But first, as always, an enormous thank you to all of the fantastic subscribers out there who help keep this program running month after month. Your support makes me feel happy and proud, and to everyone tuning in, I'm glad you're here. An additional shout out to UEC members who for the month of March receive a 15% discount at New Line Cafe, a fabulous cafe in Silver City, and a reminder that members receive 20% off most UEC programs, like the already very affordable Mornings of Mindfulness at Washington Park. You can enjoy this weekly opportunity to add movement to your Saturday mornings, add some peace with some guided stretching, hydration, and conversation. Mats are provided. All you need to do is bring comfortable clothing, a water bottle, and a mask. And for more details, you can visit the Urban Ecology Center website. Both the Maine and Costa Rica eco travel trips are filled. So if you'd like to join us on an adventure in 2023, keep an eye on the UEC website for a new batch of destinations coming soon. We do have plans to go back to Costa Rica again next year. And for the first time, we're going to be traveling to Ecuador and the Galapagos. And we're looking at maybe an extended trip within the United States, possibly with sandhill crane migration in mind. So stay tuned. On the human phenology side of things, March is celebrated as both Developmental Disabilities Awareness Month and Deaf History Month. And today is March 25th. And for whatever reason, there are just a lot of things that people celebrate on March 25th around the world. The list of holidays is just immense. I'll mention 3. Today marks the anniversary of the end of oligarchical rule and the beginning of democratic rule in 1906 in the Republic of San Marino, which for all you fans of Global and Worldle, which are the offshoots to that game Wordle, the Republic of San Marino is a landlocked country in Italy, comprised of just 24 square miles with a population of just over 33,000, making it the 5th smallest country in the world. Today is also celebrated as J.R.R. Tolkien Reading Day. So if you want to dust off your Lord of the Rings series or just watch the extended cuts of the movies, and you could probably finish them by next Friday's Backyard Naturalist if you start right now. And maybe the most important celebration today in the country where half of my ancestors came from, in Sweden, today is Waffle Day. And why is today Waffle Day? Well, it turns out that the word waffle day in Swedish, Våffeldagen, sounds a lot like the word for Annunciation Day, a religious holiday, Vårfrudagen. And so they think that people just, when people started hearing the word Vårfrudagen or Annunciation Day, subconsciously, they just kept hearing Våffeldagen, Waffle Day. And so Annunciation Day just kind of morphed into Waffle Day. And now the Swedes celebrate March 25th by eating lots of waffles. So a lot of reasons to celebrate today. And I do want to remind folks that next week's talk will be given by UW Stevens Point professor Chris Yankee, and the basis for his talk will be the March Mammal Madness event run by Arizona State University and a lot of partners. So if you have a chance to explore that website, find out a little more before next week, I encourage you to, but not necessary because it will be delightful either way because it's Chris Yankee, who is an absolutely delightful person. And one more important phenological event, starting right now and lasting until early April, some of our brightest planets are performing what National Geographic describes as a majestic celestial ballet. So if you are able to get up, this is a morning event. If you're able to get up like an hour before sunrise, and that's not hard with all these robins screaming at us at 4 a.m. And if you have clear skies to the southeast, you can witness Venus, Mars, and Saturn grouped together tightly in a ever-moving triangle. And then on March 27th and 28th, the party will be crashed, the planetary party will be crashed by a crescent moon. And then the planets will start moving from their tight triangle and morph into a straight line. And then just a few days later, Saturn and Mars will be super close, separated by a half of a degree of arc or the width of a full moon. So if you're up early, it would be worth the price of admission to see this astronomical masterpiece. And then I just have one more quick thing to mention before I move on to soil. So Backyard Naturalist subscriber Max Jitney sent me a little blurb about army ants. And by the way, I love the links that I get every week from you all. It's from past episodes, and I really enjoy. I can't get enough of them, so please keep sending them. But if you look really closely at this army ant, it appears to have an abdomen that's kind of split into two. Essentially, it looks like it has, two butts. But that second butt, the lower one, that's a little lighter in color, is actually a beetle that clamps down on that army ant right behind the pedicel there. And essentially it pretends to be part of the ant, its second butt, and it gets a free ride on the ant. And these army ants cover great distances, so scientists aren't sure if this is just a way for the beetles to get around, or if it's a way to escape the ants that want to kill it. But wow, what a specialized niche there, camouflaged as an ant rear end. So thank you, Max, for sending that to me. Okay, on to soil for real. So last week we had the pleasure of hearing from Dr. Bill Keene, and he just gave a fantastic talk on sand, and really helped by giving us a good foundation, pun maybe intended, for the talk today on soil. So feel free to go back and watch this episode on YouTube, because sand is an important part of soil. But essentially, Bill defined soil as the loose top layer of the earth that's distinguished from rock and that supports vegetation. So that's important. And to some, that's the difference between dirt and soil. Some define dirt as soil that's just totally dead. It's just the particles with no organic matter. So the moon and Mars would technically have dirt until we find life there. And then if we do, then Martian dirt would technically become Martian soil, because an important component of soil is that organic matter, not just the rock, the weathered rock. So Bill pointed out that there's 5 main ingredients in soil. You have the minerals, you have the organic matter, you have the living organisms, and then gas and water. So at the most basic level, soil is rock that has been weathered or worn down into pieces of various size mixed with organic matter. So how do we wear down the rock? What wears down the rock? There are physical processes that produce these stunning images. So you have wind that can break down rock, you have water, and then one of the really important parts of that is the freeze-thaw cycles you get in the more temperate climates. So that's physical weathering of rock into smaller pieces. And then there are the biological processes that are much more complex, and they can also break down rock, whether it's tree roots physically getting in there and breaking things up, or it's these early colonizers, the microorganisms that produce organic acids, which help to dissolve the minerals, and that weakens and then starts to disintegrate the rock. So you have the physical and the biological breaking down of rocks. And then these early colonizers will start to make a substrate that then allows other bigger plants to start taking hold. And so the little plants die, it allows for a bigger plant to move in, the bigger plants die, and then and then that kind of builds up the soil. But more importantly, the carbon dioxide that was in those plants will break down that rock even more, because it dissolves in water, and then that forms these carbonic acids that can break down the rock from a chemical process. That releases more nutrients, and then there's larger plants that live and die, create more soil, and then it doesn't take that long, if the conditions are right, for bare exposed rock, like a lava flow or exposed bedrock from various processes. In fact, in the right conditions, it can take about 100 years to go from bare exposed rocks to soil thick enough to support a full-on tree with a couple of soil horizons. So if the conditions are right, it can happen fairly quickly.
Tim, we have a quick question.
Sure.
Where does clay fall into that?
Oh, you are about to find out. Excellent question. So well, I can answer that now. Essentially, soil is broken. Soil itself, the inorganic part of soil, is just really broken down by size. And so sand is one category of sizes. So sand is, even though sand is often made from certain elements, it's really the size of the grain that defines it, that categorizes it as sand. And then slightly smaller level is silt, and then the smallest level is clay. And clay can get really, really, really small. So we had these early colonizers I mentioned. They start to make the substrate. Then the soil is essentially the medium. It's the space that holds all these nutrients. It's the space and the structure that holds all these nutrients. And then when the plants send their roots into that medium to take up those nutrients, those roots themselves stabilize that soil even more. So it ends up being this really tight, intricate, just beautifully balanced system of nutrient recycling in and out of plants, in and out of animals, in and out of fungi, bacteria, archaea, in and out of the soil itself, the non-living parts. And towards the end, we'll take a closer look at a couple of those beautiful nutrient systems. But a good, healthy, undisturbed plant-growing soil will consist of about 50% stuff, the matter, the living and non-living matter that's part of the soil, or formerly living matter, I should say, that's part of the soil. That's the stuff that's 50%. And then the other 50% is essentially space for air and water. So 50% stuff, 25% space for air, 25% space for water. And obviously that changes based on where you are and the conditions. But if you're looking for good backyard dirt soil, that's kind of what you're looking for. And then so that's where we do all these amendments and stuff to get the soil to be good for growing plants. That's the kind of sweet spot you're looking for. So here, Dr. Keene mentioned the soil triangle. So again, soils are made up of 3 different sizes of rock material, so you have sand, silt, and clay, and then the percentages of each make up the different categories in the triangle. So if you're a soil scientist, you can take a sample of soil back to your lab, you can analyze it, and then use the charts to define it. So if you're in northwestern Wisconsin, you might find Wisconsin state soil, the Antigo silt loam, Antigo silt loam. Or here in Milwaukee, we tend to have a bit more clay. Or if you're a seasoned farmer, you just pick up the soil, you rub it around in your fingers, smell it, taste it, and then you get a really good idea of what kind of soil it is, and if you should plant in it, or if you need to amend it in any way. Either way works. So just quickly looking at each of those components, sand, as we learned last week, is essentially bedrock, parent rock, that has been weathered down into grains that are between 2 millimeters and 0.05 milliliters. So if it's larger than 2 millimeters, we don't call it soil. It becomes gravel or pebbles or pieces of rock. So sand is the largest component of what we call soil. And because it's the largest grouping, you have all these various shapes and sizes. And then, as you know from being on a beach, there's a lot of airspace in between those chunks, and it makes pure sand very unstable, hard for plants to grow. It's constantly shifting. Water and everything else pretty much passes right through sand, but it does have enough of a structure to allow things eventually to grow. It can wick up water very so slightly. And most importantly, you can see grains of sand without a microscope. Then if you get rock particles that are between 0.05 millimeters at the top end and 0.002 millimeters at the small end, that's categorized as silt. And for the backyard gardeners, that's really, you want a majority of silt for your plants, for your vegetables. It's good for both drainage, it's good for retaining water. It has really nice capillary action for wicking up water from below. It's great for holding nutrients in place. It's great for the plant and fungal roots to access what's in the soil, but you can't really see the grains. But if you talk to a good soil scientist or farmer, if you chew on it, you can feel the grittiness with your teeth. And then finally, the smallest grains are characterized as clay. So again, it's not clay and silt and sand tend to be certain types of minerals, but you can have different types of minerals make up these categories. So smallest grains are clay, way too small to see unless you have a good microscope, because anything less than 0.002 millimeters in size. And because the particles are so small, there's hardly any space, like the opposite of sand with all that space. There's hardly any space for water or minerals to pass through. So clay is often a barrier, especially if it's compacted, which is why, backyard ponds are often given a clay liner. So back to the soil triangle, you can see that most soils aren't just one type. They're a combination of those grain sizes. And again, you also need the vegetable matter in as well, the organic matter. And so you have all the different categories of soils. And when you have several different predominant grain sizes mixed together, we add the word loam. So a silty loam, like our state soil is again, that sweet spot. It's fantastic for agriculture. Okay, so that's categorizing soil by grain size. And then another way that we talk about soil is the layers known as the soil horizon. So as soils develop over a long time, you start to see this layering effect. And again, the layers are known as horizons. So if you start to dig in your backyard, get a shovel or a post hole digger, garden spade even, sometimes you can see that if the soil hasn't been disturbed much over the past few decades, which is often not the case in urban backyards. Often, our backyards have been raised and platted and dug up. So sometimes it's harder to see these in the backyard. But if you dig deep enough, or if you find a place that hasn't been disturbed, you can see these layers pretty well. So starting at the top, you have what's called the O horizon. And that's essentially all the stuff that's in the initial stages of decomposition. It's the very loose, thin layer. It can be kind of thick and loose as well. But in terms of the soil layer, it's that thin layer on top. And it's essentially organic plant and animal tissue that's in that first stage of decomposition. So it's high in humus or organic matter, and humus is an important, it's a very important part of soil, and it's just an important kind of concept to think of. So humus is essentially, by definition, any organic component of the soil. So it's not alive, it was recently alive. And then some will refer to humus as the vegetative matter after it's done decomposing. So it's kind of down to its basics. But by pure definition, any of that stuff is technically humus. Functionally, this is the stuff that you'll dig out of your compost. But after like one season of your compost, you don't really have humus. You still have that more decaying layer. The humus really takes several seasons to develop in that kind of purely functional form. But it is so important to the story. It's just a very stabilizing structure. It holds things together, and it's just so important to soil food webs. And we talked a few episodes ago about how worms can be so destructive because they'll essentially get rid of that humus layer that's so important for growing seedlings and for the nutrient cycling. So the O horizon is that pretty much that top layer of fluff, that loose fluff. Again, it's so important. It for soil moisture retention, and a good healthy O layer, O horizon, is a good indicator that you have healthy soil. Then from the O layer, you go down to the A horizon, which is essentially what we would refer to as topsoil, and it's that dark soil you get from the hardware store, the plant store. It's organic matter, very rich in humus, but humus mixed with the minerals of the soil. So the A horizon is where those plant roots like to hang out. They have the quick access to the minerals, to the water, and it's where a lot of the soil animals like to hang out as well. So it's kind of the busiest layer of soil. And in the photo on the right, the A horizon is that dark, wider band below that narrow brownish O horizon band on the top. Then below the A horizon is the E horizon, also known as the eluviated horizon. It tends to be lighter in color because in this layer, most of the minerals, the irons, the aluminums, the silicate clay, they're leached down by groundwater that's running through. Not all soil profiles have this E horizon, but many do. And then underneath the E horizon is the B horizon. And I don't know, this is where I start to get cross-eyed because E doesn't come after B, and why isn't A the top layer? But for whatever reason, you have O, A, E, B. And this is what's called, the B horizon is what's called subsoil. And it tends to consist of finer particles of silt and clay that have been leached from that E layer. That makes sense because you have the E layer on top, all of these smaller things just kind of settle down into the B layer. The smaller particle, the more easily they transport downward, and they go farther down. So the bigger pieces of sand are going to stay up top. It'd be like if you took soil and put it in a glass of water, but in reverse. So in a glass of water, the bigger particles would settle towards the bottom first, and then you'd get the smaller particles moving towards the top. This is the opposite. The bigger in the soil, the bigger particles tend to stay at the top. You also have some really big ones on the bottom because of the weathering, but in the soil layer, bigger particles at the top and then finer particles in the bottom. And then there's that layer where they kind of all leach through. So it moves from the E layer down. And in fact, if you do want to look at a soil, put it in a glass of water or a jar of water, put some water in it, and you can see it settling. And again, if you're a good farmer, give it a taste. It's a very stable layer, the B layer, because these small particles hold together very well, unlike shifting sands, and it can be very compact. So if you're shoveling and you reach a layer that becomes really hard to dig through, because it's so compacted, it might be this B layer. The E layer I mentioned is eluviated because particles are leached away from it. The B layer experiences illuvination because the particles are migrating to it from above. So it's like the difference between immigration and emigration, except that you have illuviation and alluviation. In one layer they're leaving, and one layer they're arriving.
Hey, Tim.
Yeah.
I know you kind of alluded to the letters being a little confusing, but does the O stand for anything like organic?
Probably organic,
Okay.
maybe. I should know that. I would imagine, yeah. Or it's just some geologist is trying to make it hard for students to memorize these things. But yeah, E stands for alluviation, O stands for. So I'm sure there's, and geologists can tell me this, I'm sure there's the ABC, but then it's not that simple. So you add these other letters in it. So
We have one more question.
oh, sure.
if the layers of dirt move down over time, like does the A layer eventually become an E layer?
Yeah, that's a good question. It's not the layers that are moving, it's the particles that are moving. So the big fluffy stuff is always going to stay on top. And so that O horizon is always going to be there. And then by the processes, the animals moving through the soil to mix it up a little bit. But it's mainly that water drawing down, the gravity, that keeps the layers where they are. So that's an excellent place. It's not the layers that are moving, it's the particles that are maintaining those layers. There's probably a good example of that. But anyway, or like a way to think of that. Anyway, so from the B horizon, if you move down, you do get to the next letter, the C horizon. And that's essentially weathered bedrock that hasn't really been broken down yet. So it's that parent material from the bedrock below that will eventually become the soil layers that we looked at too. So it's not, I mean, it is a soil layer because there's soil in it, but there's lots of chunks of not soil in it as well, chunks of rock. And that kind of unweathered material that becomes the soil. So you look at the soil, and we'll talk about we'll talk about how that works, but the soil can only be formed from the bedrock that's either there, the parent rock, or that's brought to the area. In some places, you run into what's called hard pan, which is a layer of really hard, impermeable mineral deposits. And that's a shovel breaking, spade breaking layer. And they can be closer to the surface. They can form through different processes naturally, or oftentimes they're formed from human processes like repeated plowing, or from increased human or vehicular traffic. I think of like mountain bikes in a city park. Eventually is going to really just create this hard pan layer that's really tough, and nothing will grow in it. It just can't. So if we look at this is a picture that Bill sent me after the talk last week. This is the backyard naturalist. So this is a backyard on the east side of Milwaukee, and you can see some of those soil horizon layers. They're not super well defined, but and then he pointed out that the parent material here is glacial till. So a lot of the soil in Wisconsin is not from the bedrock, it's from the till that was brought here in the glaciers that then eventually was part of making the soil. It's both. It's not an either or. So parent material can be residual. That means it forms on site. So a good example of that is a lava flow. Now you have the rock that just formed, and then the soil that forms from that rock is going to be that igneous rock, and it's going to form from that lava flow. And then you can have parent material that's transported in either by rivers forming sedimentary rock, or again in Wisconsin, glaciers. So the glacial till is what we're seeing here. And then the third category of parent material comes from peat and peat bogs, which is kind of, that floating mass that can eventually become rock, that can eventually become soil. So, quickly just looking again at all these layers together, 4-year geology exams, the thing is it takes a long time for these layers to form, and it doesn't take long to break them down and destroy them, either at a small level by a groundhog kind of burrowing through, although the layers are still there, but mostly it's humans. And so Glenn Fredland, another UWM professor, has been doing soil cores in Riverside Park. And I should mention, you have to be very careful when digging in soils, particularly around the Milwaukee River, just because of the past pollution and cleanup. But he would do these soil cores in Riverside Park, and pretty much found very poor definition. And he really attributes that to, what happened to the park 100 plus years ago. Frederick Law Olmsted looked at the park, at the plans, and and he's very, much into accentuating and creating these natural curves and valleys and viewpoints. And so a soil core in Riverside Park in most areas is going to show very, very poorly defined soil layers because of that disturbance that happened over 100 years ago. So the park today is aesthetically pleasing, but that soil you'd almost consider brand new, even though it's been there for 100 years. And so it'll be fun to see what the students 100 years from now we'll see how that'll have changed then. So I mentioned earlier that soil is this ideal medium, not only for life, but for mineral retention and recycling. And so one of the biggest systems of mineral recycling in the soil, and one of the most important, is the carbon cycle. So carbon is the building block for life. It's required. We have carbon everywhere, but so starting with the atmosphere, in our atmosphere, you have carbon dioxide. And so you would call the atmosphere a carbon sink. So carbon can accumulate in the atmosphere just like water accumulates in a sink, but then sinks, in addition to having faucets where you can pour the water in, they have drains where the water can move out. So in a stable climate system, the amount of carbon that's being added to the atmosphere is balanced by the amount of carbon being taken from the atmosphere through all of the processes you see here. And then atmosphere is just one of the carbon sinks. So the trees, the vegetation, us, we also sequester carbon in this living layer through photosynthesis, through food consumption. And so the living layer removes carbon dioxide from the atmosphere. It adds carbon dioxide to the atmosphere. It's the faucet and the drain. Oftentimes we'll turn it into carbohydrates, and then when plants and animals die, a percentage of that carbon dioxide is released not into the air, but into the soil. And there it's quickly gobbled up by other hungry plants or decomposers. So carbon is sequestered in the atmosphere. It's sequestered in the biosphere, and it's sequestered in the soil. So the soil is part of the lithosphere. So that's a third carbon sink. And then the fourth big one is the ocean. So carbon moves rapidly and readily between these sinks, these depositories. But then, of course, what has happened in the last few hundred or even few thousand years is that humans have started to introduce new faucets. We've started tapping, opening new taps into that atmospheric sink. And we took carbon that was sequestered in a very stable form in the lithosphere, in the soil layer, as carbon as fossil fuels. So the oils and the petroleum, it was very stable there. And then we essentially opened up this new faucet between those stable areas of the lithosphere and right into the atmosphere. So carbon it's just like we opened up a fire hose, and it's filling that atmosphere with carbon way faster than it can drain out through these other processes. And then that adds to the greenhouse effect, which leads to warming, which leads to more carbon being introduced to the atmosphere from melting permafrost and other sources. And so that's really the heart of studying climate change. It's figuring out a way to start shifting all that carbon that we're releasing into the atmosphere into these other sinks, and trying to figure out how to work with the natural processes and the artificial processes to get the soil into these other sinks, the oceans, the carbon into the oceans and the soils. So we're just kind of desperately trying to slow down that fire hose of carbon dioxide that we're putting into the atmosphere. And interestingly, while burning fossil fuels gets the bulk of the blame for contributing carbon into the atmosphere, as it should, we also lose a lot of carbon from soil through agriculture. And I'm not talking about the tractors and the machines here. It's that process of tilling the soil releases a lot of carbon into the atmosphere. And we humans have been doing this for thousands of years, and eventually it accumulates. So a humus layer is very good at keeping carbon there. So as soon as you break it up, it's like, oh, the carbon's like, I'm free into the atmosphere. And scientists have estimated that since the dawn of agriculture and humans, we've released, and I have no idea how they come up with this number, but we've released 130 billion tons of carbon into the atmosphere just from tilling soils. So 130 billion tons, that seems like a lot. But then if you compare it to fossil fuels that, we've only been releasing for a few hundred years, that's 400 billion tons of carbon. So more than 3 times as much in a shorter period of time. So 130 billion tons is nothing to sneeze at. But we're taking that beautiful humus layer and just kind of shredding it to pieces and losing all those benefits. So tilling soil is really good at helping with global warming. It's also really good at breaking up all those super important mycorrhizal relationships that we're just starting to learn about. And so tilling is hard on the soil. It's bad for plants. It releases carbon dioxide. And you're starting to see a lot of smaller, more progressive farms really look at the advantages of no-till farming, and just so many advantages of it. So maybe the economic advantage isn't clear right away, but if you're talking about the systems in the world, no-till farming is another important one. So not to continue down that road of doom for too long, but another fantastic sink for carbon dioxide, as I mentioned, is the frozen humus, the permafrost. So frozen humus is even better than regular humus at keeping that carbon in. But then you have global temperatures rising, permafrost melting, more carbon being released into the atmosphere. It's that vicious cycle of warming that we're dealing with today. And even with all these in-your-face warning signs, we continue to prioritize fossil fuels. But get off that soapbox for a minute. Another really important nutrient cycle in the soil is nitrogen. So nitrogen is extremely important to plants and animals. For plants or animals, it's used to make proteins. So chlorophyll requires nitrogen. It is super abundant in our atmosphere. So it doesn't seem like something that would be a problem for plants to get nitrogen, but atmospheric nitrogen, N2, is not in a form that is usable by plants. So it needs to be fixed from the N2 gas and converted into compounds that can be used by plants. And in a healthy ecosystem or a healthy permaculture agricultural system, you have these nitrogen fixing plants, the legumes, the peanuts, the alfalfas, that can take the nitrogen out of the air and then release it into the soil and make it available to plants and then eventually animals. But as with everything, it's more complex than that, because the plants by themselves can't fix nitrogen. They have to be infected by a bacteria in order to fix the nitrogen. There's a rhizobium bacteria that then alters the plant physiology, which allows the plant to take in the nitrogen from the air and then release it into the soil. So, even the plants that get the nitrogen from the soil after it's fixed need help from these fungal mycorrhizae networks. So it's just, everything's connected to each other. And my favorite story from the mycorrhizae episode is the fungus that lures in a springtail, which is a type of hexapod, kills it and feeds it to its host tree when the host needs more nitrogen. So check that story out. But even in the nitrogen cycle, you got to get on the soapbox a little bit because of the agricultural practices, short-term profits. We're trying to skirt around this nitrogen fixing plant community. So after destroying the soil by tilling it, then we add all these fertilizers that are high in nitrogen, and that leads to just a host of other issues that compound and lead to these environmental catastrophes. So I don't know, it's like humans think that they're better than these processes that have evolved over millions of years, and we try to find these shortcuts that just mess everything up. And man, if you just leave the soil alone, it would be so much better. But I don't know, that's maybe another episode we can have over a beer sometime, or root beer, Zeke. So wrapping up the episode on soil, without even mentioning the amazing living component of the soil, but essentially we have been focusing on this since day one, right? All 2 years of Backyard Naturalists have been focused on the critters, and the soil is always a part of the story, no matter what animal you're talking about. So a lot of the organisms don't interact at that microscopic level, but the soil is that substrate they use to build their homes, like the woodchucks and the squirrels. The ants and the wasps and the worms are little smaller, but still large enough, easier to understand. Even humans like to build homes underground. And so the animals by themselves also provide an important function to healthy soil. They move particles around, they move nutrients around, they move them up and down and across layers, adding nitrogen to the soil every time you pee, which is why I try to help the forest anytime I can. But if you take a step closer from this layer, then you're talking about another, ants require 2 episodes. Like this layer would require way more. And so much of it is conceptual, and so much is we're learning. But, even when you look at like that Columbella episode, the springtail episode, the bacteria, the archaea, you have this hidden layer of predatory mites and nematodes, and it is by far the most complex food cycle in the world. There's like your nature shows on TV, David Attenborough, who I love, like those narrations that you see are nothing compared to what happens at the soil level. So it's super complex, super poorly understood. You think, okay, grassland, savanna, you've got the grasses, you've got the wildebeest, the lions, it makes for good TV, but that's happening on steroids in your backyard. Think about that next time you're enjoying a hot or cold coffee or a lemonade or something on your patio. Just try to reflect for a moment that underneath those plant layers, there is just these immense battles for life. There is these immensely complex systems happening. In the top 2 inches of a square foot of soil, there are 200 species of mites. You have carnivorous mites that are adapted as predators. And then you have herbivorous mites that are adapted to protect themselves from the predators. So like these mini T-Rexes and ankylosauruses. In 1 teaspoon of soil, I think we hear this again later, in 1 teaspoon of soil, there are more microbes than there are humans on Earth. 1 teaspoon of soil. So the layers of complexity, what's going on here, predators, herbivores, omnivores, carnivores, is just insane. And again, it's just one of those areas that we're just now starting to understand. So even the largest organism on the planet, it's not the blue whale, it's a fungus that's underground that we don't see. It's, I think, 2 square kilometers. And you'll often hear me say that, so and such organism is found on every continent except Antarctica. But even Antarctica has a healthy soil community. There are nematodes that are active 6 weeks a year in the Antarctic summer, and they live almost forever. They've like pretty much figured out this fountain of youth. They're alive. They're moving around for 6 weeks and they shut down. Then they're even then there's the predator prey interactions, the nematodes, the mites. So it's pretty ridiculous. So we will end with a nice BBC video about soils.
Soil. It's one of the most underrated and little understood wonders on our fragile planet. Here's why. Far from being lifeless dirt, it's estimated that in a single gram of soil, there could be as many as 50,000 species of microscopic organisms, or microorganisms. And in 1 teaspoon of soil, there are more microorganisms than there are people on the Earth. But much of what lies beneath in this hidden and deep universe is still alien to us. Despite being literally under our feet, humans have so far only identified a tiny fraction of the extraordinary life teeming underground. But these animals and microorganisms provide an invaluable role. Millions of years of evolutionary competition have led the microorganisms to produce antibiotic compounds to fight their neighbours. And these compounds form the basis of many of the antibiotics used by us humans. We literally make medicine from our soil. No one knows how many new treatments could be lying under our feet, waiting to be discovered. One of the most special creatures living in soil is the earthworm. Darwin was fascinated by them and said,
"It may be doubted if there are any other animals which have played such an important part in the history of the world,"
due to their importance in making and sustaining soil. Earthworms journey down and around, creating breathing holes like lungs in the soil. This creates space for plant roots to grow and keep soil alive. Under the soil, there are also vast and intricate webs of fungal threads. Plants and fungi need each other to thrive, and so they do a deal. Fungi can't capture carbon dioxide to grow like plants can, but they're better than plants at mining the soil for nutrients, so they trade. Plants give fungi carbon to grow, and fungi give plants nutrients like nitrogen and phosphorus. It's a mutually beneficial relationship, and just one example of the interconnected ecosystem we're all part of. Plant matter decays and provides food for microbes. They provide food for worms. Worms are food for birds, and so on. Soil provides us humans with almost everything we eat. But it's not just about what soils can do for us. It's important we value, appreciate, and crucially protect soil for a whole load of other reasons too. Think about this for a moment. It takes more than 100 years to build just 5 millimeters, half a centimeter of soil, but just moments to destroy through chemical contamination, urbanization, landslides, erosion, and more. Some soil is really ancient, dating back millions and millions of years. The oldest soil on Earth is thought to be in South Africa and dates back 3 billion years. In the UK, our soil is around 15,000 years old, and it formed after the last ice age. Soil is also a really valuable carbon store, capturing carbon, locking it away in stable forms deep underground. It stores 3 times as much carbon as all the plants on Earth combined, including trees. But because it grows so slowly, we need to protect what we have. We are not succeeding. We know many of the problems. Intensive farming is one of them. It releases carbon from our soils, and we're losing soil 50 to 100 times faster than it's able to rebuild. In Europe, 60 to 70% of soils are thought to be unhealthy. And in croplands in the UK, in less than 30 years from the end of the 1970s, we lost more than 10% of the carbon the soil had stored for us. And since then, well, we just don't know. Because in many countries, there's little data on soil, it's poorly protected and regulated. We grow on it, build in it, build from it. It filters and cleans our waters, reduces flooding and regulates our atmosphere. It's one of the most biodiverse habitats on Earth and a vital part of the nitrogen and carbon cycle on our planet. But the sad truth is, right now, soil hasn't enough champions fighting for it. We literally treat it like dirt. And yet there is so much untapped potential, so much wonder, and so many secrets just waiting to be discovered in the ground beneath our feet.
Thanks for watching. If you enjoyed that, be sure to check out these videos next. And if you haven't already, hit the subscribe button and click the bell.
Oh, hang on a second.
Soil. It's
I can't, stop thinking about like when you look at the soil layers and the complexity. So you think of, it's easy to visualize a rainforest with the canopy layer and the shrub layer and all of that, or the ocean, the depths and the near surface layers. And I just can't help thinking of like, so each of those layers that I was talking about are functional and you can see them, but they also provide such different conditions for the life in those layers. And so I keep thinking of like, humans try to see, well, how far can you dive in the ocean, on one breath or something like that, or we see how, like, I can imagine these nematodes like daring each other to go farther down into the I horizon or Q horizon or whatever. So I don't know, it's just really from a conceptual place, such a fun place to be, just to imagine these complexities. And again, you don't have to go far. And for me, the main takeaway is that, soils are amazing and complex and extremely important. and they really just want to be left alone to do the things they're good at, that tight nutrient cycling, the carbon sequestration, providing a loving, nurturing home for life on the planet. So encourage your farmers to look for no-tilling options to grow crops. Encourage yourself to look at no-tilling options for your yards. And let's help the soils help us to make the world a better place. So thank you very much for joining me. I'm going to stop sharing my screen.